Hi students. So today I start on popular request tutorial series on optimization. So this is like a companion to my lecture series on optimization and it will be in the optimization playlist. So what we are going to do is that for each lecture, for example lecture 1, we are going to create a tutorial. For example tutorial 1 today. Today I'm going to talk about basic definitions. I am Dr. Ranjan Ganguly. So today's tutorial we are going to focus on a few concepts. For example, the standard form of the optimization problem, what is a feasible region, what is the gradient vector, what is the Hessian matrix, what is minimum and maximum point, and what are local and global minimum points. These are also described in detail in optimization lecture 1. You can take a look at that. I'm going to put it in the end screen as well as in the description box of this video, and of course check out the optimization playlist for the full course. So let's begin with the first question. The question here is that we want to minimize a function x1 square plus x2 square while ensuring that x1 plus x2 equal to 1 and x1 square plus x2 square is greater than equal to 1. Now what we are asked to do is write this problem as an optimization problem in the standard form. Now, of course, you guys know that what's happening here is that we have an objective function which we want to minimize, and these two equations here, or rather these two expressions, they represent constraints. So we have an equality constraint and we have an inequality constraint. Now, if we want to put this problem into the standard form, we have to write it in a certain manner. So as far as the objective function is concerned, we can write it as minimize f of x is x1 square plus x2 square. Now there are two constraints here, so we can say subject to the first constraint, that is going to be hx equals x1 plus x2 minus 1. Remember, the constraint has to have the form h of x equal to 0. So here when we have the constraint as x1 plus x2 equal to 1, we rewrite this as x1 plus x2 minus 1 equal to 0. Now if we look at the inequality constraint, it's got this greater than equal to form, and for the standard form we have to convert it into the less than equal to form. So what I do is I multiply both sides of this particular inequality by -1, and so that's going to flip the sign here, and so I get this particular expression minus x1 square minus x2 square plus 1 less than equal to 0. Now this is in the form gx less than equal to 0, so I can say gx is this particular equation here. Gx is minus x1 square minus x2 square plus 1. So remember, always the standard form of the optimization problem says that minimize function f of x subject to hx equal to 0 and gx less than equal to 0. Now let's look at question 2, and question 2 tells us that we have to find the feasible region for this optimization problem, which is minimize f of x is x1 square plus x2 square subject to constraint x1 plus x2 less than equal to 1, and two more constraints. These are also sometimes known as move limits, x1 greater than equal to 0 and x2 greater than equal to 0. So in case whenever we are dealing with feasible region, we only need to look at the constraints here. So for example, though the function is given here, the function we need to minimize, the feasible region is going to be completely defined by the constraint set. So what we do is we plot these particular expressions on a graph. It's a two-dimensional problem, so we can plot it x1 versus x2, and so we see here that this is a line. Basically x1 plus x2 equal to 1 would be a line. The line would be something like this, so it would cut here at 1 0 and cut here at 0 1. So essentially this red line is the equation x1 plus x2 equal to 1. So now the points which are less than equal to 1, they are going to be below this particular line here. Now there are two more constraints here. X1 is greater than equal to 0, so that's going to give me the points on this side, and x2 greater than equal to 0, that's going to be the points on this side. So I have color coded these lines and expressions. So now you can see that the region which is encompassed by these three lines, this is given by the shaded region here, which I have made in this particular triangle, and this essentially represents the feasible region for this optimization problem. So that's how you get the feasible region. Now, of course, in this problem, the constraints were all simple linear functions. So we essentially got straight lines. They can also be nonlinear functions. Now let's look at question number 3, which is to find the gradient vector of the function f of x is x1 square plus 2x2 square plus e to the power of minus x1 minus x2. This is a function we are going to frequently use in this course. Actually, I have propounded this function in my book, and we can extend this function also by putting, for example, plus 3x3 square and putting an x3 and so on. This is a nice well-behaved function. We will see that later, but today we'll only find the gradient vector of this function. So now the gradient vector of a function is given as follows. So if we denote it by c, then it involves the partial derivative of the function f with respect to x1, x2, xn all the way, and then you have to take the transpose of this. So let's try to find the partial derivatives of this function first. So this function involves two variables x1 and x2. So I do first df by dx1. Now remember, whenever you are taking partial derivative with respect to x1, for example, you have to treat x2 as a constant. So if you treat x2 as a constant, the derivative of this term is going to be 0. So you are only going to get 2x1 here, and then you are going to get negative e to the power minus x1 minus x2. Because remember, what you are doing is you are differentiating this exponential function. So the exponential function comes here, and then this expression minus x1 minus x2 has to be differentiated with respect to x1. That gives the negative 1 here. So that's the expression here. Now if we take df by dx2, then we are going to get 4x2 minus e to the power minus x1 minus x2. So again, in the case of the second partial derivative, I treat x1 to be a constant. So the derivative of the term x1 square is going to be 0. Now once I get these two derivatives, I can write it in a vector form. So c will be this vector. The first term is going to be df by dx1, and the second term is going to be df by dx2 as given out in this particular definition. Remember, this definition has the transpose here, which is used to make it simple to write out that expression for c. Now question number 4 tells us that find the Hessian matrix of this function f of x, the same function as we looked at in the previous example. So the definition of this H matrix is given here. So this is the second differential. So for example, the diagonal terms are simply f differentiated with respect to x1, x2 all the way to xn twice. And then we see the off diagonal terms. For example, the term in 1, 2 is derivative with respect to 1 and 2. The term in 1n is derivative with respect to 1 and n, and so on. So you get the hang of this particular matrix. Now, of course, given a problem of dimension 2, we are going to be only considering the first two term here, or this term, this term, this term, and this term. That is the first two rows and first two columns. So of course we have obtained the derivatives in the previous example for the gradient. So now what we do is we take the second derivative. So again, to take the second derivative with respect to x1, this will become 2, and then plus e to the power minus x1 minus x2. Then again, derivative of f with respect to x2 for the second time, that will become 4, and then plus e to the power minus x1 minus x2. Now remember, these positive signs are coming because I'm differentiating these expressions here with respect to x1 or x2, and that's throwing a negative sign back at me. Also, I can get these partial derivatives here. For example, if I take the term here, df by dx1 differentiate with respect to x2, this term is going to be 0. The second term is going to give me e to the power minus x1 minus x2. I put all these things together. So if you look at this particular submatrix here, I get that here. And so this matrix in green is the H matrix, which is widely used as far as Taylor series approximations of multivariate problems are concerned. So now let us continue with this question set, and let us look at some graphical problems. So for example, in this particular problem, I want to find graphically the minimum and maximum points of this function, or rather the minimum point of this function. So the function is x4 minus 2x squared plus 1, and I have to do it graphically. I do not need to know any necessary or sufficient conditions at this point. So let us try to do that. I have plotted this function in Excel. You can plot it in something else also. Maybe if you're using Python, you can use matplotlib, or you can do it in MATLAB or Mathematica. And I get this nice function here. You can clearly see that there are two local minimum points here. These are the local minimum points, and this would be like a local maximum point. Of course, this function is not bounded at these two ends, so it keeps going up in both directions. So if we do not have any bound, then these are essentially unbounded maximum points also. But the minimum point, certainly these two are the local minimum points of this function. Now finally, the last question is that graphically find the local and global minimum of this function. Again, we are not going to use any calculus here. We simply have the function, so we can plot it. The function is x4 minus 4x squared plus x. Let's plot the function here, and I get something like this. I have again done this in Microsoft Excel, and you can clearly see that here there is a global minimum point, here there is a local minimum point of this problem. Now in such problems, what can happen is that various numerical methods may actually converge to this local minimum point if you are starting in this particular region, and they may convert to this minimum point here if you are starting in this particular region. Now many functions, or I should say some functions which are out there in realistic engineering design problem, may have global minima, may have local minima, in which case you would probably be better off getting the global minima. Of course, in this function case, we see that the positive root is here, or the positive minima is here, and this one corresponds to a negative value of x. So again, there may be cases where this may not be an admissible point for some practical reason. So today we reviewed some of the basic concepts which we have seen in lecture 1, for example, standard form of optimization problem, the feasible region, gradient vector, the H matrix, minimum and maximum points, and local and global minimum point. Again, take a look at my optimization lecture 1 for all the theory, and also look at the optimization playlist for the full course for this particular subject, and do subscribe to my channel if you have already not done so, and I will see you soon in optimization tutorial 2.